Okay, so welcome back to the third session. My name is Andreas Löschel. I'm from the Ruhr-University in Bochum. Very happy to be here and being able to chair this session on sustainable solutions. We have three speakers, and we are going to tackle, I think, very important problems in the German energy transition. Try to push again, or I go closer. So in my case, okay, it's green light is on, so you should hear. It's well, it's on. Yeah, the green light is on. No. We should make sure that they can as well hear us online. Good. Okay, so we have three speakers. As I said, we're talking about sustainable solutions, and we are going to have presentations that are dealing with different aspects. The first two are dealing with, I think, two policies in sectors that are really crucial for the energy transition. That is on energy retrofits and industry subsidies. We have talked today a lot about the EU emissions trading system, with carbon pricing as a cornerstone of the energy transition in Europe. But of course, there are all these other sectors that are not under the EU ETS. And currently, the big debate about how this is going to move ahead with the ETS2, the second carbon pricing scheme in these sectors, transportation, building, and part of the industry. And of course, the carbon pricing scheme will not be the only measure that is going to be used in these sectors, in buildings, in industry, and we are going to hear ex post analysis on two instruments in detail. The one on industry transformation, where we are going to hear more about the subsidization of investments in terms of increasing R&D and evidence that we see here, and the other one is on energy retrofits and their impacts on expenditures and emission. The first one will be here Victor Kahn from ParisTech, who is going to present us with some evidence from these programs. As I said, this is part of policy packages, so it's really important to understand whether this is successful or not. And we will see that indeed the industry transformation thing is successful, but it's probably not very well targeted. That's another issue, of course, with subsidies. We have to use our money wisely, and this is not only an issue for the member states, but also for the Europe as a whole. And some of these things seem to be really expensive. And this is another insight from the first paper on the retrofits, where we as well will see that yes, this is working, but it comes at probably relatively high cost, with relatively little impacts in terms of CO2 emissions, and in any case with a much lesser economic impact than we would expect from the engineering studies that are available on these topics. And then we have a third presentation by Jorge Uribe. Jorge, which is on pricing risk of weather in renewable energy generation. That's, of course, as well a very important topic that is now related to renewable energy and how we are actually pricing these renewable energy better. In Germany, we want to move towards market-based build-out of renewables in this decade, actually probably even earlier with power purchase agreements, bilateral agreements with industry in order to support the rollout of renewables. And of course, what you are going to present us in terms of the role of weather conditions on these projects, I think will be crucial to understand, and therefore many research institutions are as well now looking much more on these natural conditions, and how they can be used and probably addressed as well in market designs. So I think this is an interesting session, and we have I think, reserved 15 to 20 minutes for each of the presenters, and we will have some time for questions afterwards, so hold your breath. I'm going to start with, if I succeed, with Victor's presentation. Where? Modo pantalla completa. Estupendo. Entonces, vamos a ver. You're the first. Okay, good. Victor.
Thanks, Andreas, for the presentation. Thanks, everyone here for attending my presentation, and thanks to the organizing team for giving me the opportunity to present my works. So today I'm going to speak about a paper which is part of my PhD thesis, which is supervised with Mathieu Glachon. And I'm going to speak about the effect of home energy renovation on residential carbon emission and residential energy expenditures, using panel data from France. So first, why is this topic important? I mean, for me, this is important for two main reasons. The first one is that, as you can see here, buildings represent almost half of the energy consumption in France. Here is that's the data in France, but I mean it's more or less the same everywhere in Europe. So it's a general issue. And if you look only at residential building, it represents more or less 1/3 of energy consumption. So buildings represents a big field in order to reduce energy consumption and carbon emission. Besides, several engineering models have tried to assess the profitability of different technologies in order to reduce energy consumption, in order to reduce carbon emissions. Here you have the model of the McKinsey company, and on X you have the potential carbon emission each technology can reduce, and on Y you have the cost per ton of carbon avoided regarding each technologies. And then here on the left part of the graph you have negative cost of carbon. It means that even in a world where global warming does not exist, when there is no climate change, all these technologies should be profitable anyway. So on one side you have a big energy consuming sectors, and on the other side you have technologies which are profitable, because if you look at these technologies, you have building insulation, lighting system, air conditioning, water heating, which are all technologies related with home energy retrofits. So normally you should expect all the actors to invest massively in these home energy retrofit technologies. But actually it's not the case at all, and that is called the energy efficiency gap, the gap between what actors should do if they were like I forget my word, but if they were looking for economic profitability, and what they actually do, it means they do not invest at all. So you have a lot of literature, theoretical literature, which try to explain the origin of this gap. Often they're talking about asymmetry of information, or about households that have not enough liquidity in order to invest, in order to explain that why don't households invest in energy efficiency. But actually, the literature about assessing the ex-post real profitability of all these technologies are much more scarcer. So you have some studies which try to assess the energy retrofit impact with ex-post econometrics analysis. Some were laudatory with energy retrofit, some were less. But the reference studies, the one run by Foley, Greenstone, and Wolfram in the Michigan states in the USA, using randomized controlled trials, were very raised the big critics on the home energy retrofit, saying that The real impact of home energy retrofit in this policy in Michigan, which was targeting low-income households, was overestimating by 50% the real impact of the technologies it was funding. So what do we do with Mathieu? Is that we want to see in France what is the average effect of, what is the average ex post effect of residential home improvement on energy expenditures and carbon emissions. And so in order to do so, we use brand new estimators with a different approach, and an estimator proposed by Descriptive and Dotfeuille in 2020. And we are using a household panel data between 2000 and 2013 in France. So let's present the data we use in detail. So we use a panel done by the TNS Sofres, which is the French Polling Institute for the ADEME, which is the French agency for energy transition. And in the panel, each household was interviewed every year about its energy behavior. So how much do you spend in electricity consumption, gas consumption, fuel oil consumption, and other kind of fuel? But also, there was the question, do you have invest in energy renovation? And if you have invest, how much do you have invest, and which kind of technology do you have invest? And household could select amongst 21 categories about Windows-related investments, wall insulation, roof insulation, heating system investments, etc. So we have 21 categories of work we are analyzing. The panel is unbalanced. That's one of the weaknesses of our data. So we only keep households that stay at least 4 years in a row in our panel. And in our restricted panel, we have 1,000 more or less households we follow each year. And amongst those 1,000 households, during the period of study, 1/3 have had at least one energy retrofit investment. So here is the data about the energy consumption, the energy expenditures and the carbon emission for retrofitter households and non-retrofitter households. And there is two important things to see in this data. First, there is no real correlation between energy expenditures and carbon emission. Energy expenditures is led by power consumption, while carbon emission are more led by fuel oil consumption and gas consumption. So that's why it is interesting to look at the same time both at effect of energy retrofit on expenditures and effect of energy retrofit on carbon emissions. And the other thing which is important is that, as you can see, the non-retrofitter households consume more power, more electricity than retrofitter households, which are more consumer of gas and fuel oil. So we will have to control in our analysis by the main heating fuel used by each household, because otherwise, if you have a price differential inflation during the period of study between, for instance, electricity and gas, and that's the case, you will be biased if people using more gas are having more retrofit operations. So here, it's the data about which kind of operation are made. So in our study, there were like 805 retrofit operations made by the household. On average, they were spending like 5,000 euros in this renovation. And as you can see, like 47% of half of the renovation are Windows-related operation, and 40% of the operation are heating system-related operation. That's another weakness of our study, because today the portfolio has widely changed, and it's more like 50% insulation works, 40% heating system works, and 10% Windows-related works. I am speaking about the French portfolio of renovation. So now, what is our strategy of identification? So we are using a two-way linear fixed effect model. And if we were using a naive two-way fixed effect model, we would be biased. It has been shown for 3 or 4 years by several theoretical econometricians that we will have a bias because we are using a continuous treatment variable, so the amount of investments. So that's why we will be using a binary variable, which is having made investments or not having had energy retrofit investments. We are also biased because if we use a naive approach, we are also biased because we have a different variation in timing of treatment. So people are not having the energy retrofit operation at the same time in our period of study. You can have it in 2001, 2002, 2003, etc. So that might introduce a bias. And also, you will be biased with a naive approach because if you have heterogeneity across time, and we can think that on the energy innovation, you are likely to have this kind of heterogeneity because you might have learning effects of households after they have had energy renovation. So in order to solve all these bias, we are using the DID-L estimator proposed by Tchorzewska and Dotfei in 2020, which is robust to all these issues. I will try to explain a little bit more after what is the main idea of these estimators. So here is our equation regression. So we are looking at the effect alpha L, which estimates the impact L years after having had energy retrofit on the logarithm of energy consumption and residential carbon emissions. We have a vector of control. I will explain in the next slide what are the control variables. We have a region year fixed effect which control for exogenous shock at a regional level, such as weather or macroeconomic shock. And we have the main heating fuel year fixed effect, which I spoke about in the slide about the energy consumption. And here you have a household level fixed effect. So the main things about the Tchorzewska estimator is this condition. So in our regression, we are looking only at households. We are only comparing households that has had energy retrofit at the year L year before the estimation for alpha L, and with non-already retrofitter households. So in the naive approach, we will be comparing only people that as their treatment changing. So you will be comparing, for instance, treated households with already treated households, and so that will be biased. And so here we are only comparing treated households, newly treated households, with non-already treated households. Also, I have to add that we drop households because households can have in our panel several retrofit operations. So once they have a second retrofit operation, we drop them from the panel. So we keep only one times retrofitter or never retrofitter household. So we have two potential sources of endogeneity. The first one, I call it the Greta Thunberg effect. So you watch a conference of Greta Thunberg about global warming. She's very convincing. And so you say, okay, global warming is something very important. So I'm going to reduce my energy consumption, but I also want to improve the efficiency of my home. And so at the same time, you will reduce your energy consumption and you will have energy retrofit. So your ex-ante consumption will be biased. So for test for this endogeneity, we have an ex-ante parallel trade assumption with a placebo test that the estimator of Tchorzewska allows us to have. And the second endogeneity effect is the baby effect. So if you're expecting a baby, you're likely to have to renovate your home and, for instance, to have a home energy retrofit, but you're also likely to increase your consumption right after having the baby. So your ex-post consumption will be linked with the cause of your ex-ante retrofit. The baby effect is also important with, for instance, the retirement, which has the same kind of effect. And so for this, we have several control variables, so the household size, maybe for the baby effect, and the household head activity status, for instance, for the retirement. And we also control for income in our panel. So there I'm going to present the result. So here, that's the effect of our treatments on energy expenditures. So how do you read this graph? You have the year -1, that's the last year before having energy renovation. So by construction, the effect is 0 because it's the reference year. And here, in 1, it's 1 year after having renovated. It's the difference between retrofit household and non-retrofit household compared to the -1 time. So here you have a significant effect, which means that 1 year after having had retrofit household has decreased by 5% their energy consumption compared to non-retrofitter households. The effect is stable over time. And here you have the placebo test. So it's the same thing, but here it's comparing people that will have energy retrofit in 3 years with people that will not have energy retrofit in 3 years. And as you can see, the coefficient is not different from 0. So the ex-ante parallel trade assumption stands. Here you have the same result for the residential carbon emission. Is the same, even though it is less precise with the carbon emissions. I didn't talk about the year 0. It's not very interesting to look at the year 0 because households can have energy retrofit in January and in December. So the year where people have the energy retrofit is not very interesting and not very significant neither. So to sum up the results, we have so for people having energy retrofit reduced by 4.7% their energy consumption and by 5.1% their residential carbon emissions. Both effects seems to be stable over time. And on average, people are spending 5,000 euro in energy retrofit. So it means that for 1,000 euro, you reduce by 13 euro your energy expenditures, which is very, very low. I mean, it's not profitable at all, even without any discounting rate. So it tends to question the energy engineering models about energy efficiency. Also, we did this quick analysis, which, so the C2E scheme is the main policy about energy renovation in France. So it is worth more or less 3 or 4 billion euros per year. And the policy defines for each technologies a savings for 1,000 euro invested. So for instance, for installation, the C2E scheme says you will save 91 euro per year. And so with our estimation, we have 13 euro per year, and we are actually out of bounds regarding the ADEME C2E model estimation. So in conclusion, we strongly advocate to revise engineering models used in daily regulatory practice, at least in France. We thought that all this public policy, very ambitious public policy, should at least have ex post validation or ex post control about their real efficiency. And that's not the case at all for the moment in France. For the next step, we want to look at the heterogeneity amongst retrofit technologies. Maybe insulation is more efficient than windows or heating. So we want to look at this effect. And also, I want to talk about the limits of our analysis. So first, the data is old, now almost more than 10 years old. We do not take into account the comfort in our study. And comfort might be very important, especially regarding public health, since 1 degree more in houses is something has a significant impact on winter diseases. And also, in our analysis, we have considered that energy retrofit, that the whole cost of the whole investment was concerning energy retrofit, but you could consider that energy retrofit is only about the premium you pay for most efficient technologies compared to a standard technology, especially regarding to windows or to heating systems, since you cannot consider that households can live without windows or heating systems. So thanks a lot for your attention, and if you have any question after, I will be pleased to answer you.
Perfect. Thanks a lot, Victor, for the presentation. And as said, we are going to collect questions at the end. So let's move to the second one, which is Kinga from the Center for European Economic Research, and the floor is yours.
Thank you, Andreas. Thank you also for a beautiful introduction. I hope I can still have something to add, but the summary was perfect. Hello, everybody. I'm Kinga Tchorzewska. I'm a postdoctoral researcher at ZEW Mannheim, University of Mannheim, and I'm a research associate at Uribe and chair of energy sustainability. As some of you know, I used to be a PhD student here, and so I participated in many symposiums in the past, but it's the first time that I'm here as a speaker, and I'm very honored and very happy to be back, especially after this pandemic time. And today I will be talking about a paper entitled The Direct and Indirect Effects of Environmental Investment Subsidies on Green Innovation. And it's a paper that studies a subsidy scheme that was aimed at incentivizing adoption of green technologies. And so what we were trying to do here with my co-authors, Mariana Marino and Pierpaolo Parota, is to see how this the subsidy scheme encouraged different adoptions of green technologies, looking at those response in a way, and then also whether this subsidy scheme had some unintended indirect effects also on R&D. So to give you a general analysis of environmental investment subsidies, just to give you a recap. Obviously, subsidies are attractive because they deal with the capital market failure, right? They translate into a smaller cost to the company. And then, especially given that the private returns associated with the new technologies are unclear, subsidies in many ways, they mediate this uncertainty. So it is said that it kind of also balances all of those environmental considerations that we have in our mind with the concerns about competitiveness that, for example, environmental taxations might have. And then they produce clear environmental and social returns, so there's higher social welfare. But of course, subsidies are not all wonderful. There is a question of whether they might result in opportune use of public expenditures because we need to finance them somehow. There's a question of whether there is a crowding in and crowding out, so whether firms use subsidies even though they would have invested in those adoption of those green technologies anyway, and whether there is a technology lock-in, right? Because this policy instrument is not as flexible. Firms do not use their private information on what technology is the best, but simply use one of the technologies that are available and is encouraged by the regulator. And given the time constraints, I'm not going to go through a whole literature review, but just to give you an idea, there are some papers, of course, that study the effects of environmental policies on adoption of green technologies, but there is a little focus on two key issues. One is that we know very little on what would be the optimal dose of environmental subsidies. And second one is exactly what are the unintended effects of environmental subsidies. Here I build on the last chapter of my PhD thesis, where I studied an environmental investment tax incentive in Spanish setting. So what do I do in this paper? The aim is to investigate the effects of a proportional increase, so-called dose response, in the environmental investment subsidy on green investment and green innovation. So first we make a distinction between the adoption of green technologies at the firm level, and then also the environmental R&D that the firm performs. And then within those intended effects, so the direct effects on adoption, we look both at end-of-pipe technologies and cleaner production technologies. And for those of you that know, end-of-pipe technologies are just technologies that reduce pollution at the end of the production pipe, so they're not energy efficient. They're actually considered inferior to cleaner production technologies that are more energy efficient. They reduce the use of natural resources, and then as a result also the emission levels. And then we also study the unintended effects, so the level of environmental R&D that the firm produces. And here we make a distinction between internal and external green R&D. With this aim in mind, we use a panel data set of 1,915 industrial firms between 1999 and 2011 in the Netherlands. And in this data set, there are firms only that have received an environmental subsidy because, as you know, it's tautological to say that if a firm receives a subsidy, it will invest in green technology. So we only focus on this kind of dose response proportional increase. And we use two methods. One is just the fixed effects. So here is the proportional and dose response effect, looking at the percentile of subsidy that the firm receives, and the nearest neighbor matching. And here we look at the ATT and the dose response effect. In the Netherlands, you can see that since the 80s, energy policy has been the cornerstone of the Dutch strategy. They seem to be one of the most generous countries when it comes to the environmental policy indicators. They have a large number of subsidy programs, and it exists under this umbrella scheme that is called Sustainable Energy Transition Incentive Scheme. And so different technologies, they have to compete under a single budgetary ceiling. And it's managed by the Ministry of Economic Affairs and Climate Policy by the Netherlands Enterprise Agency. So the objective of this scheme is to encourage firms to make environmental investments such that obviously the environmental friendly technologies are involved and that the environmentally friendly technology is less expensive than alternative polluting technologies, and those investments are made in the Netherlands. And this subsidy scheme is funded through a surcharge on electricity and gas use. So to arrive at our unique data set, we have combined two unique firm level surveys at the Statistics Netherlands. One is called the production cost, and the other one is environmental costs of firms. And it's an unbalanced panel over 12 years with a total of over 18,000 firm year observations with representative industrial sectors at 2-digit level. And it includes a series of variables. So on the side of PS, it includes capital assets, turnover, indebtedness, operative income, value added, expert status, and other subsidies. And then what is important for this paper, ECF includes environmental investment data plus environmental subsidies. And this is important because we have a series of variables on which we can match very well. And then we have very rich dependent variables that we can assess. So just to give you an idea, the majority of the firms, they have between 20 to 50 employees. And as you can see also from the firm sectors. Most of our companies, they produce metal products or machines, apparatus, wood, paper, which is representative of the Dutch industry. So the survey is very good at representing the state of affairs in the Netherlands. And then an average environmental subsidy is around 4,000 euros. And then our outcome variables, so the investments for adoption, they're around 14,550 for total, and then 5,800 for cleaner production, and over 8,000 for end of pipe. And then the environmental R&Ds are a bit smaller at 4,500, 1,200 level. Okay. So to give you an idea of our main specification, we log our treatment variable and our dependent variable, and of course a challenge in this analysis that voluntary policies such as this one may suffer from self-selection. So problems such as natural willingness of firms to get the subsidies. So in this paper, we're trying to go around this and just focus on firms that already received environmental subsidies, and then just look at the proportional effect, and hence we use the log levels, and of course we use the firm fixed effects. Okay, so to have a look at the first results. Here we have the effects on cleaner production technologies, so then on the superior production, the more energy efficient technologies, and we look both at the proportional effects, so this is the first line above, and then in the two rows below, we have the indicator function that represents a level of environmental subsidy that the firm received, that is, if it's above the 50th percentile and above the 75th percentile. And as what we can see is that the results are stable across, no matter whether we use the control variables, the lag-dependent variable, and firm fixed effects, and it's positive and statistically significant at the 99% level. And there is a 70% increase in investment as you increase the environmental subsidy by 1%. And then we can see also that this effect is the highest the level of environmental subsidy that the firm receives. And then when we focus on the end-of-pipe technologies, we can see that actually the coefficients are much larger, and especially as the level of environmental subsidy increases, which shows that environmental subsidies, the higher they become, the firms are more likely to actually invest in end-of-pipe rather than cleaner production technologies, so the better targeting of the subsidy in place is needed. And then when we turn our attention to the internal R&D, again, we have positive and statistically significant coefficients on those unintended effects, and there are a bit smaller, those table, and they are also there for the external R&D, so for the outsourcing of R&D. And then we also carry out this analysis for nearest neighbor matching, and our results are stable. And we carry out several robustness checks and extensions to make sure that our results are stable. So we look at the different methods of estimation, the first differencing in the outcome variables. We remove the crisis years to make sure that those do not affect our analysis. We carry out heterogeneity with respect to firm size, so small and large, and we show that larger firms typically show significantly larger direct and indirect effects. and that also larger firms invest more in cleaner production in comparison to smaller firms. And then we also carried out heterogeneity with respect to firm energy intensity, low, medium, high. So to conclude, in this analysis, we go beyond the general assessment of environmental investment subsidies on adoption of green technologies and green innovation, and we find that in general the Dutch subsidy was successful at increasing both clean air and production and end-of-pipe technologies, but as you increase the amount of the subsidy, a firm is more likely to invest in end-of-pipe technology, and this is not desirable, so the better targeting is much needed. And lastly, the internal R&D is more easily encouraged through the use of environmental subsidies than R&D, and the sufficient dose is at the 50th percent. Thank you so much.
Excellent, Kinga. Thanks a lot for presentation and for keeping the time. So we now move to Jorge as the last speaker. Who's going to talk on pricing weather risks. And here you are. Jorge, please.
Thank you very much. Thank you for attending my presentation. Sorry. No. Thank you very much for attending my presentation. I'm going to talk about this paper that it started like a single author project, but now it's becoming bigger. I'm going to tell you how. It's about pricing the risk of weather or weather conditions on renewable energy generation projects. So some of the contribution that I do here is that I propose like a methodology to price the risk in this kind of projects. For example, the generation of electricity through wind turbines or through solar cells. This is the main contribution, and this is especially like important or relevant for these kind of projects or companies that lack long historical records. Why? Because in finance, I'm more like a finance guy, we are used to perform this risk assessment and this pricing of the risk of a project using like long and rich information for similar projects or for similar companies. And here in this world, everything is new. So many times, or relatively new, and many times you don't have these benchmark data sets, and you don't have these long historical records. So you need to resort to a different approach to measure risk. So basically what I do here is that I adapt some concepts from finance. One is the value at risk, which is very used in the financial industry. And the second one is the expected shortfall or tail value at risk. And I'm going to tell you how in the present context. And to illustrate this methodology, which is the main contribution, the methodology itself, to illustrate the contribution, I use real data for 3 cities in Spain, Barcelona, Madrid, and Valencia, with different coordinates and different weather conditions, but the same price, of course, because it's a single price. But then I also extended this, and this is in collaboration with my research team, for other 37 cities in Europe to show like how this will work in different contexts. The main motivation is the one that I already told you. And also that for this energy transition that we are in the middle in, to be sustained, from my point of view, it has to be like the incentive of the private sector needs to be in line with those of the public sector, because there are political constraints and cycles, and we don't want this to be dependent on these cycles. We also want to be lined up in all the stakeholders. And the second motivation is the one that I already told you, that there is no rich information to conduct this risk assessment of this kind of projects. The main methodological insights are, okay, the financial information, for example, think of a prosumer, a generation of electricity which works, for example, in a small neighborhood, and they want to generate the electricity. And they want funding for this project. Or you are a company and you are doing something which is new in the sector, and you go to the bank or you go to the insurance company, and you need like a product, because one of the main risks that you have is that you cannot generate all the electricity that you need to operate or for your needs in your household. And when you go there, they don't really have how to access the risk of this project, because they don't have enough information like other companies or other projects which are similar. So this is true, but it is also true that in this case, and it's going to be like this even more in the future, you do have information about one of the key variables, and like rich information about weather records. And these weather records, you can use them to conduct this risk assessment that otherwise you will continue using the financial information that is lacking. So here, I'm going to focus, everything is from a risk perspective. So there is a huge literature in energy economics and in the energy field that use like weather, for example, to forecast electricity prices or this kind of outcomes. But here I'm going to focus on the risk facet. So it's not about forecasting or understanding like an average scenario of generation. It's about understanding what is going to happen when there are like adverse weather conditions and you cannot generate enough electricity for your needs. So this is the second insight. We need to focus on this risk perspective. And the way in which I'm going to do that is through conditional quantile regressions. They are very popular tools like in finance and nowadays also in insurance. And this is a way to move from the traditional mean of the average effect to understand the tails of the distributions. So this is just to give you an example. This is like a random plot that I could use here. If you, generally in economics you are, or in any area you are working here, you want to see like the average effect, you are to see like the average generation. But for a risk perspective that I'm gonna follow, you are more interested in these tails of the distribution. So you are interested, for example, if this was a generation, the electricity generation, you will be interested in this case when you cannot generate enough electricity. So instead of looking at the mean, at the average here, we are going to look at one tail here. And for this reason, I'm going to use a quantile. And a quantile is just an ordered statistic. I'm pretty sure that you are familiar with the name. It's an ordered statistic that divides the sample in equal size parts. And for example, you have here very low quantiles and here very high quantiles. So this is what I'm going to put here. So the quantile regression is in the same lines. In the average case, you have like a traditional OLS regression, when you have to explain the average, for example, of the irradiance that is used to generate electricity. And here you have some covariates, which could be weather, because this electricity is a function of the weather conditions and the irradiance that is recorded at the Earth's surface in any given day. But instead of looking at this average case here, I'm going to look at the quantile case. So I'm going to focus on the risk scenarios when you generate too few electricity, perhaps for your needs. So in terms of methodology, the first part of the methodology consists of selecting a key variable, because I'm working here from the perspective of an insurance company. The insurance company, for example, wants to offer a product for a neighborhood or a small firm that is generating what it needs in terms of energy. And they want to know how much they are going to charge for this product. So we need like a key variable that is going to determine how much we are going to price. And the key variable that I selected was irradiance, because here in this example, I'm working, for example, on the perspective of an insurance company and a product for solar cells, for solar generation. So irradiance is the key variable. And it's public as well. You can go to solar, you can go to NASA Power, and you can get this data. And you also can get data about the weather conditions here in the second bullet point that you need to understand what is going on with irradiance. So you need to model irradiance, and in particular, you need to model these bad or adverse scenarios of irradiance and generation of electricity. For this second, you use this covariate. I selected this from previous work, like temperature, precipitation, and wind speed. And they are very good at predicting that. We are going to see that, and especially in the tails of the distribution, especially in the quantiles or the risk perspective. So I'm interested in very low quantiles. For example, the 5% of the worst scenarios in the sample, because those are the scenarios that the insurance company is interested in, because they want to know how are going to charge, and it depends on how much they have to pay to you when there is this adverse scenario in which you don't generate all the electricity that you need. So you are going to receive a payment by the insurance company. So this is what we need to do here, be interested in this very low quantile. And then, of course, we have daily data. So we have daily data for weather and also daily data for this irradiance and the generation itself. But when you are an insurance company, because this was partially funded by a competitive project in MAFRE Foundation, so we were having conversations about this. When you want to sell this product, you need, for example, like a contract for a year. So you are not going to pay every day to the person. You are going to pay like when there is an event during a year. And then you need to charge as well something in relation with this same frequency. So you have daily data, and you can use this data to understand the risk of the generation based on weather. But you also need to transfer at the end the premium that they are going to charge to an annual basis. So I use like a second value at risk. So I'm going to model the value at risk or the quantile, the very low generation scenarios on a daily basis. But then I'm going to take the worst of these scenarios to select or to set when there is an event that the insurance company is going to pay for. And with this, once I have modeled this, the generation, I can price how much this is going to cost to the insurance company. And the way I'm going to do that is that after I have these very worst scenarios here, I calculated the losses for the insurance company, remember, from the perspective of the insurance company. And this is a value to the market prices of the day when this event was recorded during the sample period. So this is very similar to what the banks use to measure systemic risk or something like that. It's like a tail value at risk, how much you are going to pay in these worst scenarios. But here is different because I'm conditioning everything to the realizations of the irradiance, whether they are even worse than those that I was forecasting or predicting using the weather conditions. And when this happens, I recorded a loss and I valued this to the market prices. Once I do that, everything is like straightforward. Here, for example, in the results, which are very short because the main contribution was to say how to do that, how to do this pricing. I use, this is an ordinary OLS regression, like a linear regression. And we can see that for the 3 cities in my sample, the 3 weather variables that I'm using are very good at predicting these average cases. But this is only to motivate the selection of these 3 variables. But these are actually the results for the quantiles. Here you have the effects of these three weather variables on irradiance and therefore on the generation of electricity by solar cells. And here you have the quantiles themselves. So those are periods of very high generation. So the high quantiles is when you generate a lot, perhaps more of what you are gonna need. And those are the very low generation scenarios. And those are the interesting one from the perspective of the insurance company. Because in these cases, you are gonna see that you need to pay the premium in some of these cases, the worst of these cases. And as you can see here, this is also to motivate this approach, is that this is highly non-linear. What you get in the middle, the red line with the dotted lines, this is the ordinary least squares regression. It's like the linear regression that I showed you in the last slide. So as you can see, this has nothing to do with the real behavior of the weather and the effects of the weather on this irradiance. Is totally non-linear from this perspective. So you need to model specifically this tail. You cannot model the average case and then move to the tail using like a normal transformation or with the standard deviation. You cannot do that because you are gonna miss all the effect and all the dynamics that is actually determining when you have to pay the premium. This is for one city. This is for Madrid, and this is for Barcelona. And as you can see, the effects, for example, if you look at this, they are similar, but not totally the same. For example, look at precipitation. It's different. So when you apply this methodology to different geographical coordinates, you are going to get very different results. And this is good, because this is going to allow to the insurance company to target like a more appropriate price, depending on where this generation is going to take place. Finally, finally, almost. This is like a summary. This is what I do here. I model this value at risk, or this very low quantile of irradiance. And of course, this is very seasonal, because weather is seasonal and irradiance as well. So you get like these peaks during the winter. But then in some of these cases, you get like the very worst cases when you have to pay for this event. And these are more or less, you cannot forecast that, but you can value that. Because when this happens here, and if you have like an energy needs, I didn't model this properly, because it depends on the project, because you are the one that knows how much energy you need, and you have to forecast that. Here I just simulate some energy needs, and then with this variable and this simulation of the energy needs, you can have like the generation deficit. When this generation deficit is so high that you need like a compensation from the insurance company, is when this product becomes attractive. So with this, it's possible to get a table like this one here, which is just like, okay, which is the value at risk of all these in these cases. How many times you get like violations of this value at risk, so these very low generation scenarios that you are interested in. And then you can have like the cost of the average event, because in these events you are going to have to pay, and then you can take the average, how much did it cost in the past, and you can charge like a function of this number here, which is the annual premium. But this is just like a multiplication by the number of events that you expect to observe during a certain year. Okay, this is, of course, these numbers here are just like an illustration of the true value, because it depends on the technology, and assuming like a very standard solar cell technology, but the generation that you can get is different depending on the technology. This could be used as well to price the risk of a wind turbine or a different kind of generation. So this is just like illustrative. But what you can do is this here, which is the extension that I wanted to share with you as well, that we are working in right now, is that you have a huge variation if you apply this methodology to different cities in Europe. As you can expect, here you have Stockholm, and this is in relative terms, for not to focus too much on the euros, but in the difference, in the cross-sectional difference in different cities in Europe. For example, if you are here, more or less, you get the 3 cities of my first example, Valencia, Barcelona, and Madrid, and the premium and the cost of this insurance project is very similar in these 3 cities because it's the same market price and the weather conditions are also not that different. But when you go to the whole Europe, you get this huge variation here. And this is important from the perspective of the insurance company, because this means that you can also charge, not only that you should charge different prices for the same project in different countries, which is natural, but also that is possibly you are gonna get diversification benefits for offering this product in different coordinates, because they always want to avoid what they call catastrophic risk, which is that they have to pay for the insurance for the product at the same time to all the consumers, which is very likely if you think of weather conditions, because weather conditions are fundamental of all the projects. So whenever you observe a bad outcome in terms of generation for one project, you can observe the same for many of them. But this risk is reduced. Oh, sorry. So that's all. This is only to conclude. This is the same, basically, that I was telling you before. So thank you very much for your attention.
Excellent. Thanks a lot for this presentation. So I think we have time for a quick round of questions. So, okay, so I have
Thank you very much for your interesting presentations. I have one question for Jorge. Just to better understand, why are you considering the location of the cities and not the location of the countryside where most renewable plants used to be? And related to that point, it's likelihood that when we have more sun or more wind in one time, the grid can become congested, so you should apply some curtailment, and depending in the framework, there is a lower income for the owner of the plant. So are you considering these 2 issues, the location of the plant and the grid conditions that can constrain your production? Thank you.
Should I answer right away or at the end? Okay, yes, definitely. It's just like an illustrative example, but we are also considering different, like many other geographical locations when the actual projects are used. What we wanted to do, our main goal at the end is just to say, okay, here is this tool, and you only need to provide the coordinates where the project is going to be located, and you get the price that you need to charge for this project. It's not that, like, for us, this is kind of weird because this is like something exogenous. Our data is exogenous. It's only like we have this methodology and you get the price, but for sure in real life, you need to go where the project is going to be located. Regarding the second question, I'm not sure if this answers you, but we are also considering the possible, in a follow-up project, the possible diversification benefit that you can also get by combining all these, the 2 sources of energy generation, wind and solar cell, because the correlation between them is not 1. So you can get like diversification benefits as well if you not only have like a portfolio of products for solar cell, but if you expand this as well to other variable renewable, definitely. Thank you.
Okay, I have a question for Kinga for the second presentation. I have found very interesting this assessment of the unintended effects or indirect effects on R&D. But as you know, R&D is not in end at itself. No? You do R&D to get more innovations. And I wonder if you can, in your analysis, go a step further. I mean, to analyze the effects of this increase in internal and external R&D on new innovations or on eco-innovations? You have this panel data of 12 years, and maybe dividing or splitting the period, you can see what is happening with this increase of R&D, because external and internal, because this distinction is very interesting, because the subsidies.
Yeah, so the problem is that we cannot really, I'm not really sure whether we can connect it perfectly, because we do not have information on what type of exactly activities they're performing R&D on. So it's an interesting idea that we will maybe discuss, but I'm not quite sure if that's possible.
Okay, so last question, Michael.
Okay, this is a question for Victor, or, well, a sort of, it's not so much a question as a trying to understand the results. So your findings are that the benefits, there are essentially very few benefits to the individuals of installing these energy-saving measures, that the costs vastly outweigh the expected financial return. But then, you know, the question really is, are these numbers telling us something which is that it's not worthwhile thinking about these things, or is it that implicitly we're not valuing the carbon cost nearly highly enough? That it, you know, the cost of the carbon is not really being borne by the consumers, and therefore they're not seeing the returns from reducing that carbon.
Yeah, I mean, in my estimation, I did not calculate any carbon costs with this estimation, but yeah, of course, the real efficiency of energy retrofit will depend on the value you put on carbon avoided cost. But the other question, it might be also, okay, maybe that the carbon cost is not enough high, but we can also think about cost of opportunity. So maybe energy renovation is not the most efficient way to reduce the faster as possible energy consumption and carbon emission. And maybe other sectors, I'm going to tell something, but like, I'm not sure. Only for an example, for instance, have an electrification of the core pork might be something more efficient than energy retrofit in home. And so that's finally our final remark, our final question is, maybe we're having very ambitious policies in energy retrofit, but we do not see and we do not evaluate the impact of these policies, and maybe we could wonder ourselves if there is not other solution or other sectors which could also benefit from ambitious subsidies policies. That's the way I think we have to interpret our results.
Excellent. So I think we have to close now because we're already running over time. Thanks again for these nice presentations, and also for the Q&A, and you do it bilaterally afterwards, because now we are going to have the final presentation, and that is chaired is Jose, and we will hear Ben Suvakul. Excellent. Okay, thanks again.